A black hole is a region in space where the gravitational pull is so strong that nothing, not even light, can escape from it. This phenomenon occurs when a massive star collapses under its own gravity at the end of its life cycle. The concept of a black hole is rooted in Einstein's theory of general relativity, which predicts how massive objects distort the fabric of space-time. The boundary around a black hole, known as the event horizon, marks the point of no return. Once an object crosses this threshold, it is inevitably pulled into the black hole. The event horizon is not a physical surface, but rather a mathematical boundary, beyond which escape velocity exceeds the speed of light. At the center of a black hole lies the singularity, a point where gravity is thought to be infinite, and space-time curvature becomes infinitely large. The singularity represents a breakdown of our current understanding of physics. It is a region where the known laws of physics cannot describe the conditions. Black holes can be categorized based on their mass. Stellar mass black holes form from the remnants of massive stars, typically ranging from a few to several tens of solar masses. Supermassive black holes, on the other hand, are found at the centers of galaxies and can be millions to billions of times more massive than the Sun. Intermediate mass black holes are a hypothetical class that might bridge the gap between stellar mass and supermassive black holes. They are thought to form in star clusters or through the merger of smaller black holes. Observational evidence for intermediate mass black holes is still being gathered. Micro black holes or primordial black holes are another theoretical possibility. These would be much smaller and might have formed in the early universe. Detecting such black holes would require observing their effects on surrounding matter and radiation. The concept of black holes was first proposed in the 18th century by John Michel and Pierre-Simon Laplace, who speculated about dark stars with strong enough gravity to trap light. However, the modern understanding of black holes developed significantly in the 20th century, particularly with the work of Carl Schwarzschild, who provided the first exact solution to Einstein's equations. Hawking radiation, a theoretical prediction by Stephen Hawking, suggests that black holes can emit radiation due to quantum effects near the event horizon. This radiation could cause black holes to lose mass and eventually evaporate over incredibly long timescales. This idea links black holes to quantum mechanics, offering insights into the fundamental nature of reality. Despite their name, black holes are not entirely invisible. Their presence can be inferred by observing the behavior of nearby stars and gas. When a black hole interacts with its surroundings, it can produce powerful X-ray emissions and energetic jets, making it detectable with modern instruments. Black holes play a crucial role in the evolution of galaxies. The supermassive black holes at galactic centers can influence the formation and dynamics of stars and gas within their host galaxies. The process of black hole growth through accretion and mergers can also provide clues about the history of the universe. Observations of black holes have advanced significantly with the development of sophisticated telescopes and detection methods. The Event Horizon Telescope, for instance, captured the first image of a black hole's event horizon in 2019, marking a milestone in astrophysics. This image provided direct visual evidence of a black hole and its surrounding accretion disk. Gravitational waves, ripples in spacetime caused by violent events like black hole mergers, have opened a new window for observing these cosmic phenomena. The detection of gravitational waves by LIGO and Virgo collaborations has confirmed the existence of binary black hole systems and provided insights into their properties. Studying black holes helps scientists test the limits of general relativity and explore the fundamental nature of gravity. These cosmic objects serve as natural laboratories for investigating extreme conditions that cannot be replicated on Earth. Insights gained from black hole research can enhance our understanding of the universe and the laws that govern it. Black holes also inspire a sense of wonder and curiosity in the public imagination. Their mysterious nature and the dramatic events associated with them capture the interest of people around the world. Popular culture often features black holes in movies, books, and other media, reflecting their impact on human creativity and storytelling. Ongoing research continues to uncover new aspects of black holes, challenging and expanding our knowledge of the cosmos. As technology advances, future discoveries will likely shed more light on these enigmatic objects, revealing deeper connections between the fundamental forces of nature. Black holes form from the remnants of massive stars that have exhausted their nuclear fuel. When a star runs out of fuel, it can no longer support itself against the pull of its own gravity. For stars much more massive than the Sun, this collapse leads to a dramatic supernova explosion. In a supernova, the outer layers of the star are blown away, while the core collapses under gravity. If the core's mass exceeds about 3 times the mass of the Sun, no known force can stop the collapse, and it forms a black hole. This process happens rapidly, within seconds. And another way black holes can form is through direct collapse. In this scenario, a massive star collapses directly into a black hole without a supernova explosion. This usually occurs in stars with very low metal content, where radiation pressure is insufficient to cause a supernova. Black holes can also form from neutron star mergers. When 2 neutron stars orbit each other closely, they gradually spiral inward due to gravitational wave emission. Eventually, they collide and merge, forming a black hole. This process produces a burst of gravitational waves detectable by observatories like LIGO and Virgo. Primordial black holes are a theoretical possibility that could have formed in the early universe. Fluctuations in the density of matter shortly after the Big Bang might have led to regions collapsing into black holes. These black holes could range in size from microscopic to several times the mass of the Sun. Accretion is a key process in the growth of black holes. When matter falls into a black hole, it forms an accretion disk as it spirals inward. Friction and gravitational forces heat the material, causing it to emit radiation, often in the X-ray part of the spectrum. This process allows black holes to accumulate mass over time. Mergers of black holes also contribute to their growth. When 2 black holes come close enough, they can become gravitationally bound and merge. The resulting black hole has a mass roughly equal to the sum of the original black hole's masses, minus the energy emitted as gravitational waves. Supermassive black holes are believed to form through the merging of smaller black holes and accretion of vast amounts of gas. These black holes reside at the centers of galaxies and can grow to millions or even billions of times the mass of the Sun. Their formation and growth are closely linked to the evolution of their host galaxies. Star clusters provide another environment where black holes can form and grow. In dense clusters, frequent interactions between stars can lead to collisions and mergers, producing black holes. These black holes can then sink to the center of the cluster and merge with others, increasing in mass. Some black holes may form from the collapse of very massive stars, known as population 3 stars. These stars, which formed in the early universe, had low metallicity and could reach masses much larger than those of stars today. Their collapse could directly produce black holes without a supernova explosion. Black holes can also result from the collapse of massive stellar remnants known as Wolf-Rayet stars. These stars have lost their outer hydrogen layers due to strong stellar winds, exposing their helium cores. When these cores collapse, they can form black holes. In addition to forming from stars, black holes can also form in the dense environments of galactic nuclei. Here, high densities of stars and gas provide ideal conditions for black hole formation and growth. Collisions and interactions in these regions can lead to the creation of new black holes or the merging of existing ones. As black holes form and grow, they can influence their surroundings in significant ways. Their intense gravitational pull can affect the orbits of nearby stars and gas clouds. The energy emitted from accretion disks can also heat and ionize the surrounding gas, impacting star formation. The formation of black holes is a fundamental process in the universe, contributing to the dynamics and evolution of galaxies. By studying black holes and their formation, scientists gain insights into the life cycles of stars, the behavior of matter under extreme conditions, and the history of the cosmos. Advances in observational technology, such as gravitational wave detectors and high-resolution telescopes, are enhancing our understanding of black hole formation. These tools allow us to detect and study black holes in greater detail, revealing new aspects of their origins and growth. Black holes come in various types, classified primarily by their mass and formation process. The 3 main categories are stellar mass, supermassive, and intermediate mass black holes. Each type plays a unique role in the cosmic landscape and has distinct characteristics. Stellar mass black holes are the most common type, formed from the remnants of massive stars. These black holes typically range from a few to several tens of times the mass of the Sun. They form when a star undergoes gravitational collapse at the end of its life cycle, often after a supernova explosion. Supermassive black holes reside at the centers of galaxies and are millions to billions of times the mass of the Sun. Their origins are still a topic of active research, but they likely grow through the accretion of gas and mergers with other black holes. These giants have a profound influence on the formation and evolution of galaxies. And intermediate mass black holes are thought to bridge the gap between stellar mass and supermassive black holes. These black holes range from hundreds to thousands of solar masses. Observational evidence for them is still sparse, but they are believed to form in dense star clusters or through the merger of smaller black holes. Micro-black holes, also known as primordial black holes, are a theoretical class that could have formed shortly after the Big Bang. These black holes could be much smaller than stellar mass black holes, potentially even microscopic. They are a subject of intense theoretical investigation, as their existence could provide insights into the early universe and fundamental physics. The characteristics of black holes also vary based on their spin and charge. Most black holes are expected to have some degree of rotation due to the angular momentum of their progenitor stars. The spin of a black hole affects the structure of its event horizon and the behavior of matter in its vicinity. Charged black holes, or Reissner-Nordström black holes, are another theoretical possibility. These black holes possess an electric charge which influences their gravitational field. However, most astrophysical black holes are expected to be nearly neutral, as they would quickly neutralize their charge by attracting oppositely charged particles. Rotating black holes, or Kerr black holes, are more common in the universe. The rotation creates a region outside the event horizon called the ergosphere, where space-time is dragged around the black hole. This effect, known as frame dragging, can extract energy from the black hole, a process theorized by Roger Penrose. Binary black holes are systems where two black holes orbit each other. These systems emit gravitational waves as they spiral inward and eventually merge. The study of binary black holes has provided valuable information about the properties of black holes and the dynamics of their mergers. Ultramassive black holes are an extension of supermassive black holes, with masses exceeding 10 billion solar masses. They are found in the cores of the largest galaxies and galaxy clusters. These colossal black holes challenge our understanding of black hole growth and galaxy formation. Wandering black holes are those that have been displaced from the centers of their galaxies. They can be ejected during galaxy mergers or through interactions with other massive objects. These black holes roam the interstellar space, and detecting them is a significant observational challenge. The diversity of black hole types reflects the complex processes that govern their formation and evolution. Each type of black hole provides a different window into the workings of the universe, from stellar evolution to galaxy dynamics. Understanding these types helps astronomers piece together the history and structure of the cosmos. The study of black holes also intersects with various fields of physics, including general relativity, quantum mechanics, and high-energy astrophysics. By exploring the different types of black holes, scientists can test theoretical predictions and uncover new physical phenomena. Advancements in technology, such as gravitational wave observatories and space telescopes, are expanding our ability to detect and study black holes. These tools are revealing the diversity and complexity of black hole populations, offering new insights into their nature and behavior. Research into black holes is a rapidly evolving field, with new discoveries constantly reshaping our understanding. As we uncover more about the different types of black holes, we gain a deeper appreciation for their role in the universe. This ongoing exploration promises to unlock many more mysteries about these fascinating objects. Black holes are defined by several key properties that distinguish them from other cosmic objects. These properties include mass, spin, and charge, which together determine the behavior and structure of a black hole. Mass is the most fundamental property of a black hole. It influences the size of the event horizon, the boundary beyond which nothing can escape. The mass of a black hole can range from a few times that of the Sun to billions of solar masses. The event horizon is the defining feature of a black hole. It is not a physical surface, but a point of no return. Anything that crosses the event horizon is inevitably pulled into the black hole, including light, making the black hole appear black. Singularity is the core of a black hole, where gravity is thought to be infinitely strong, and space-time curvature becomes infinite. At the singularity, known laws of physics break down, making it one of the most mysterious aspects of black holes. Spin refers to the rotation of a black hole. Most black holes rotate because they inherit angular momentum from their progenitor stars or through accretion of matter. The spin affects the shape of the event horizon and the space-time around the black hole. The ergosphere is a region outside the event horizon of a rotating black hole. Within this region, space-time is dragged along with the black hole's rotation, allowing for the possibility of energy extraction from the black hole through processes like the Penrose process. Charge is another property of black holes, though most astrophysical black holes are nearly neutral. A charged black hole would have an electric field in addition to its gravitational field, but it would quickly attract oppositely charged particles to neutralize its charge. Hawking radiation is a theoretical prediction that black holes can emit radiation due to quantum effects near the event horizon. This radiation causes black holes to lose mass and energy over time, potentially leading to their eventual evaporation. Accretion disks form around black holes when matter spirals inward before crossing the event horizon. These disks are heated to extremely high temperatures, emitting X-rays and other radiation. Accretion is a primary way for black holes to grow in mass. Jets are powerful beams of particles and radiation that can be ejected from the regions around black holes. These jets are often observed in active galactic nuclei and can extend for thousands of light years, impacting their surroundings significantly. Gravitational waves are ripples in space-time produced by accelerating masses, such as merging black holes. The detection of these waves has provided a new way to observe black holes and understand their properties, including their masses and spins. The no-hair theorem states that black holes can be fully described by only three parameters: mass, spin, and charge. This simplicity belies the complex processes that occur around black holes, but it is a cornerstone of our theoretical understanding. Tidal forces near a black hole can be extreme, stretching and compressing objects due to the intense gravitational gradient. This effect, known as spaghettification, would be lethal to any object or person approaching too close to a black hole. Escape velocity at the event horizon of a black hole exceeds the speed of light, which is why nothing can escape once it crosses this boundary. This property fundamentally defines the nature of black holes and their inescapability. Black hole thermodynamics explores the parallels between the laws of thermodynamics and the behavior of black holes. Concepts like temperature and entropy can be applied to black holes, leading to deeper insights into their nature and the fundamental principles of physics. Understanding the key properties of black holes helps scientists unravel the mysteries of these fascinating objects. These properties not only define the black holes themselves, but also influence their interactions with the surrounding universe. Through ongoing research and observation, we continue to uncover the complexities and wonders of black holes. One of the most famous black holes in astronomy is Cygnus X1. It was one of the first black hole candidates discovered and is located about 6,000 light-years away in the constellation Cygnus. Cygnus X1 is in a binary system with a blue supergiant star from which it accretes matter. Another well-known black hole is Sagittarius AI, the supermassive black hole at the center of our Milky Way galaxy. It has a mass of about 4 million times that of the Sun and is located approximately 26,000 light-years from Earth. Observations of stars orbiting Sagittarius A have provided strong evidence for its existence. M87A, the supermassive black hole at the center of the galaxy M87, gained fame when the Event Horizon Telescope captured its image in 2019. This historic photograph showed the black hole's shadow and its surrounding accretion disk, offering direct visual evidence of a black hole. V404 Cygni is another notable black hole in a binary system, located about 7,800 light-years away. It made headlines in 2015 when it experienced a series of powerful outbursts, emitting X-rays and visible light. These outbursts provided valuable data on black hole accretion processes. GRO J1-5540, also known as the Jewel Box, is a microquasar located about 11,000 light-years away. It is one of the few black holes with jets observed in the Milky Way, and its study has helped scientists understand the mechanisms behind jet formation in black holes. LIGO and Virgo have detected several merging black holes through gravitational waves, each providing unique insights. One of the most famous is GW150914, the first ever direct detection of gravitational waves, resulting from a merger of two stellar mass black holes, about 1.3 billion light-years away. XTE J11650-500 is one of the smallest black holes known, with a mass of about 3.8 times that of the Sun. Located about 10,000 light-years away, it has provided important data on the lower mass limit for black holes and the behavior of matter in extreme gravitational fields. IC10X1 is a stellar mass black hole in the dwarf galaxy IC10, about 2.2 million light-years away. It is notable for its high mass, around 30 times that of the Sun, and its rapid X-ray variability, which offers clues about the processes occurring in its accretion disk. Centaurus A, or NGC 5128, hosts a supermassive black hole at its center with a mass of about 55 million times that of the Sun. Located 12 million light-years away, it is one of the closest active galaxies to Earth, and is known for its prominent jets and radio emissions. NGC 1365 is a barred spiral galaxy with a supermassive black hole about 2 million times the mass of the Sun. Located 56 million light-years away, it has been studied extensively with X-ray telescopes, revealing details about the black hole's spin and surrounding accretion disk. ESO 24349 HLX1 is an intermediate mass black hole candidate, one of the few known, located in the galaxy ESO 24349. Its mass is estimated to be around 20,000 times that of the Sun. It has provided valuable data on the possible formation mechanisms of intermediate mass black holes. Ophiuchus X1 is a stellar mass black hole located about 14,000 light-years away in the constellation Ophiuchus. It was one of the first X-ray sources discovered and has been a key target for studying the properties of black holes and their X-ray emissions. NGC 1277 is a galaxy with an unusually large supermassive black hole comprising about 14% of the galaxy's total mass. Located about 220 million light-years away, it challenges current models of black hole and galaxy coevolution, suggesting alternative formation pathways. H1821 plus E643 is a quasar hosting one of the most massive black holes known, with a mass of about 30 billion times that of the Sun. Located about 3.4 billion light-years away, it provides an extreme example of black hole growth and the energetic processes in quasar environments. The black hole in the galaxy NGC 4151, often referred to as the Eye of Sauron, is one of the most well-studied active galactic nuclei. Located about 62 million light-years away, its relatively close proximity has allowed detailed observations of its accretion disk and central engine. Gravitational waves are ripples in space-time caused by some of the most violent and energetic processes in the universe. They were first predicted by Albert Einstein in 1915, as part of his theory of general relativity. These waves are produced by accelerating masses, such as binary black holes or neutron stars in orbit around each other. When a massive object moves, it distorts the fabric of space-time around it. If this object accelerates, the distortions propagate outward at the speed of light, much like how ripples spread across a pond. These propagating distortions are what we call gravitational waves. Gravitational waves carry energy away from their source, allowing us to detect and study the events that created them. The amplitude of these waves decreases with distance from the source, making them incredibly weak by the time they reach Earth. This is why detecting them requires extremely sensitive instruments. The first direct detection of gravitational waves was made by the LIGO collaboration in 2015. This landmark discovery confirmed Einstein's prediction and opened a new era of astronomy. The detected waves originated from the merger of two stellar mass black holes, located about 1.3 billion light-years away. LIGO, the laser interferometer. Gravitational Wave Observatory uses laser interferometry to detect these minute distortions in space-time. By measuring the tiny changes in the distance between two widely spaced mirrors, LIGO can detect gravitational waves passing through Earth. Gravitational waves provide a new way of observing the universe, complementing traditional electromagnetic observations. They offer insights into phenomena that are otherwise invisible, such as black hole mergers and neutron-star collisions. This new observational window allows us to study the cosmos in unprecedented detail. The information carried by gravitational waves is encoded in their amplitude and frequency. These characteristics can reveal the masses, spins, and other properties of the objects involved in the generating events. This data provides valuable information about the dynamics of extreme astrophysical processes. Gravitational waves are not just produced by black hole and neutron star mergers. They can also be generated by other violent events, such as supernovae and the rapid rotation of neutron stars. Even the Big Bang itself is thought to have produced primordial gravitational waves, which could offer clues about the early universe. The detection of gravitational waves requires sophisticated technology and international collaboration. Besides LIGO, other observatories like Virgo in Europe and Kagra in Japan are also contributing to this effort. Together, these observatories form a global network, increasing the chances of detecting and accurately locating gravitational wave sources. One of the remarkable aspects of gravitational waves is that they interact very weakly with matter. This means they can travel across the universe without being absorbed or scattered, carrying pristine information about their sources. This property makes them a powerful tool for studying the universe. Gravitational wave astronomy is still in its infancy, but it holds great promise for future discoveries. As detectors become more sensitive, we expect to observe a wider variety of sources and gain deeper insights into the fundamental processes shaping our universe. Each new detection helps to refine our understanding of physics under extreme conditions. The study of gravitational waves also has implications for our understanding of fundamental physics. For instance, these observations can test general relativity and strong gravitational fields, and explore the nature of gravity itself. They may even provide hints about the unification of gravity with the other fundamental forces. Gravitational waves have already led to significant breakthroughs, such as the observation of neutron star mergers. These events produce both gravitational waves and electromagnetic radiation, allowing for multi-messenger astronomy. This combined approach can reveal the detailed physics of phenomena like colossal and the production of heavy elements. Future gravitational wave detectors, such as the space-based LISA mission, will open up new possibilities for observing low-frequency gravitational waves. These waves are produced by sources such as supermassive black hole mergers and will provide a new perspective on the formation and evolution of galaxies. Understanding gravitational waves and their sources is a major scientific goal of the 21st century. As we continue to explore this new frontier, we will uncover more about the nature of our universe, from the behavior of black holes and neutron stars to the very origins of space and time. The history of gravitational wave discovery dates back to Albert Einstein's prediction in 1915 as part of his general theory of relativity. Einstein proposed that massive objects accelerating through space-time would create ripples, known as gravitational waves. Despite this groundbreaking idea, Einstein himself doubted that these waves could ever be detected due to their incredibly weak nature. In the 1960s, Joseph Weber pioneered efforts to detect gravitational waves using resonant bar detectors. Weber's experiments, although unsuccessful in providing concrete evidence, laid the groundwork for future research and sparked interest in the field. His work demonstrated the potential for detecting these elusive waves and inspired a new generation of physicists. The 1970s saw significant theoretical advancements, particularly in understanding the sources of gravitational waves. Scientists realized that binary systems, like pairs of neutron stars or black holes, would be strong emitters of gravitational waves. This realization guided the design of more sensitive detection methods, focusing on these powerful cosmic events. Russell Hulse and Joseph Taylor's discovery of the binary pulsar PSR B19913 plus 16 in 1974 provided indirect evidence for gravitational waves. Observations showed that the pulsar's orbit was gradually shrinking, exactly as predicted by Einstein's theory due to energy loss from gravitational wave emission. This discovery earned Hulse and Taylor the Nobel Prize in Physics in 1993. In the 1980s and 1990s, advancements in laser interferometry paved the way for more precise detection techniques. Kip Thorne, Ronald Drever, and Rainer Weiss were instrumental in developing the concept of using laser interferometers to detect gravitational waves. This idea led to the establishment of the Laser Interferometer Gravitational Wave Observatory, or LIGO. LIGO's construction began in the 1990s, with facilities built in Livingston, Louisiana, and Hanford, Washington. The initial phase of LIGO aimed to demonstrate the feasibility of detecting gravitational waves with laser interferometry. Despite not achieving detections during its initial run, LIGO provided valuable data and experience for future improvements. The early 2000s saw the development of advanced LIGO, a significantly more sensitive version of the original detectors. Advanced LIGO's enhanced capabilities included improved optics, more powerful lasers, and better isolation from ground vibrations. These upgrades increased the likelihood of detecting gravitational waves from cosmic sources. On September 14, 2015, LIGO made the first direct detection of gravitational waves, a groundbreaking achievement that confirmed Einstein's century-old prediction. The detected waves came from the merger of two black holes, each about 30 times the mass of the Sun, located 1.3 billion light-years away. This event, known as GW 914, marked the beginning of gravitational wave astronomy. The discovery of GW 914 was announced to the public on February 11, 2016, sparking widespread excitement and media coverage. This historic detection not only confirmed the existence of gravitational waves, but also opened a new window for observing the universe. The event demonstrated the power of laser interferometry and validated decades of theoretical and experimental work. Following the first detection, LIGO continued to observe more gravitational wave events, including additional black hole mergers. Each detection provided new insights into the properties and behavior of black holes. The accumulation of these observations began to reveal patterns and statistics about the population of stellar mass black holes in the universe. The Virgo detector in Italy joined LIGO in 2017, enhancing the network's ability to pinpoint the location of gravitational wave sources. The collaboration between LIGO and Virgo allowed for more precise sky localization, making it easier to identify potential electromagnetic counterparts to gravitational wave events. On August 17, 2017, LIGO and Virgo detected gravitational waves from the merger of two neutron stars, an event known as GW 170817. This event was also observed across the electromagnetic spectrum, from gamma rays to radio waves, marking the first instance of multi-messenger astronomy. The observations provided valuable information about the production of heavy elements and the behavior of matter in extreme conditions. In 2017, the Nobel Prize in Physics was awarded to Rainer Weiss, Barry Barish, and Kip Thorne for their decisive contributions to the LIGO detector and the observation of gravitational waves. This recognition highlighted the significance of their work and the impact of gravitational wave discoveries on our understanding of the universe. The history of gravitational wave discovery continues to evolve, with ongoing improvements in detector sensitivity and the addition of new observatories. Future projects, such as the space-based LISA mission, aim to detect gravitational waves from even more sources, including supermassive black hole mergers. These advancements promise to expand our knowledge of the cosmos and the fundamental nature of space-time. Gravitational waves play a crucial role in astrophysics by providing a new way to observe and understand the universe. They carry information about cosmic events that cannot be obtained through traditional electromagnetic observations. This unique perspective allows scientists to study phenomena like black hole mergers and neutron star collisions in unprecedented detail. The detection of gravitational waves has opened up the field of multi-messenger astronomy. By combining gravitational wave data with electromagnetic signals, astronomers can gain a more comprehensive understanding of cosmic events. For example, the simultaneous observation of gravitational waves and gamma-ray bursts from neutron star mergers has provided insights into the production of heavy elements. Gravitational waves offer a direct way to measure the properties of black holes. By analyzing the waveform of the detected signals, scientists can determine the masses, spins, and distances of the black holes involved in mergers. This information helps to build a clearer picture of the population and evolution of black holes in the universe. Neutron star mergers detected through gravitational waves provide valuable data on the behavior of matter at extreme densities. These events offer a unique laboratory for studying the properties of nuclear matter and the equation of state of neutron stars. Observations of these mergers help to refine models of neutron star structure and composition. The study of gravitational waves allows scientists to test general relativity in strong gravitational fields. By comparing the observed waveforms with theoretical predictions, researchers can confirm or challenge Einstein's theory. So far, gravitational wave observations have been consistent with general relativity, but future detections may reveal new physics. Gravitational waves help to map the distribution of black holes and neutron stars in the universe. By detecting these events across different regions of space, astronomers can infer the locations and densities of compact object populations. This information is crucial for understanding the formation and evolution of galaxies and star clusters. The detection of gravitational waves from binary black hole mergers provides insights into the dynamics of these systems. Observing multiple mergers allows scientists to study the mechanisms that bring black holes together, such as dynamical interactions in dense star clusters, or the evolution of binary star systems. Gravitational wave astronomy contributes to the study of cosmic evolution. By observing events at different distances, researchers can trace the history of black hole and neutron star mergers over billions of years. This timeline helps to understand how these objects have influenced the growth and development of galaxies. Gravitational waves also offer clues about the early universe. Primordial gravitational waves, if detected, would provide direct evidence of processes occurring shortly after the Big Bang. These signals could reveal information about inflation, phase transitions, and other fundamental events in the universe's infancy. The role of gravitational waves extends to the search for exotic objects and new physics. Detecting signals from hypothetical objects like primordial black holes, cosmic strings, or dark matter interactions could transform our understanding of the cosmos. Gravitational wave observations may uncover phenomena that challenge existing theories and inspire new models. Gravitational waves have a significant impact on the study of high-energy astrophysical processes. The energy released in events like black hole mergers and neutron star collisions is immense, and gravitational waves carry this energy across vast distances. Studying these waves helps to understand the mechanisms driving these powerful events. The precision of gravitational wave measurements allows for detailed tests of gravitational theories. Deviations from expected waveforms could indicate new physics or modifications to general relativity. These tests are crucial for developing a deeper understanding of gravity and its interactions with other fundamental forces. Gravitational wave observations enhance our knowledge of stellar evolution. By detecting the end stages of massive stars, such as black hole and neutron star formation, scientists can refine models of how stars live and die. This information is essential for understanding the life cycles of stars and the enrichment of the interstellar medium. The international collaboration in gravitational wave astronomy fosters advancements in technology and methodology. The combined efforts of observatories like LIGO, Virgo, and CAGRA lead to continuous improvements in sensitivity and detection capabilities. This collaboration ensures that the field remains at the forefront of scientific discovery. As gravitational wave detectors become more sensitive, the range of detectable events expands, offering even more opportunities for discovery. Future observatories, both ground-based and space-based, will continue to revolutionize our understanding of the universe. The role of gravitational waves in astrophysics will only grow, unlocking new mysteries and deepening our knowledge of the cosmos. Detecting gravitational waves requires extremely sensitive instruments due to the incredibly weak nature of these signals. The primary method used today is laser interferometry, a technique that can measure tiny changes in distance between mirrors separated by kilometers. LIGO, the laser interferometer. Gravitational Wave Observatory consists of two large interferometers located in the United States. These facilities use high-powered lasers to detect minute changes in the distance between mirrors placed 4 kilometers apart. When a gravitational wave passes through, it distorts space-time, causing a slight shift in the mirror's positions. Virgo is another interferometer located in Italy, working alongside LIGO to detect gravitational waves. Virgo's design is similar to LIGO's, but its arms are 3 kilometers long. By working together, LIGO and Virgo can more accurately pinpoint the location of gravitational wave sources. KAGRA, located in Japan, is another significant interferometer contributing to the global gravitational wave network. What sets KAGRA apart is its underground location, which helps to reduce seismic noise, and its use of cryogenic mirrors to minimize thermal noise. Space-based interferometers like the upcoming LISA mission aim to detect gravitational waves with even lower frequencies than ground-based detectors. LISA will consist of 3 spacecraft forming an equilateral triangle with sides millions of kilometers long. This configuration will allow LISA to detect supermassive black hole mergers and other cosmic events. The sensitivity of these interferometers depends on their ability to isolate the mirrors from external vibrations and noise. Advanced seismic isolation systems, such as suspension systems and active feedback controls, are crucial for reducing ground noise and improving detection accuracy. Quantum noise, arising from the uncertainty principle, is another challenge for gravitational wave detectors. Techniques like squeezing the quantum states of light can help to reduce this noise, enhancing the sensitivity of the detectors to weak gravitational wave signals. Calibration and data analysis are essential aspects of gravitational wave detection. Precise calibration ensures that the measurements are accurate, while sophisticated algorithms analyze the data to identify potential gravitational wave signals amidst the noise. Another detection method involves timing arrays of pulsars, known as pulsar timing arrays, PTAs. These arrays use the precise timing of pulsar signals to detect gravitational waves passing through our galaxy. PTAs are particularly sensitive to gravitational waves with very long wavelengths. The European Pulsar Timing Array, the North American Nanohertz Observatory for Gravitational Waves, and the Parkes Pulsar Timing Array in Australia are leading efforts in this area. By monitoring many millisecond pulses over long periods, these projects aim to detect the subtle disturbances caused by gravitational waves. Future ground-based detectors like the Einstein Telescope and the Cosmic Explorer are being planned to further increase sensitivity and expand the range of detectable events. These next-generation observatories will feature longer arms and improved technologies, pushing the boundaries of gravitational wave astronomy. Data from gravitational wave detectors are shared and analyzed globally, with scientists from various fields collaborating to interpret the signals. This collaborative approach enhances the reliability of detections and maximizes the scientific return from each observed event. Gravitational wave astronomy relies heavily on computational power for data processing. Large-scale simulations and machine learning algorithms help to model potential sources and identify gravitational wave signals in the noisy data collected by the detectors. Public engagement and citizen science projects also play a role in gravitational wave detection. Platforms like Einstein Home allow volunteers to contribute their computing power to the search for gravitational waves, helping to process vast amounts of data. As detection methods and technologies continue to evolve, the field of gravitational wave astronomy will expand, revealing new insights into the universe. The constant improvement and innovation in detection capabilities promise to uncover more about the fundamental nature of space-time and the dynamic events that shape our cosmos. Gravitational waves are crucial for studying black holes because they provide direct evidence of these enigmatic objects. Unlike electromagnetic signals, gravitational waves are produced by the movement of massive objects and can travel through space without being absorbed or scattered. When black holes merge, they emit gravitational waves that carry information about their masses and spins. By analyzing these waves, scientists can determine the properties of the merging black holes, such as their mass and rotation speed. This data helps to understand how black holes form and evolve. Gravitational waves also reveal the dynamics of black hole interactions. Observing the waveform of the gravitational waves allows scientists to reconstruct the orbits and final merger of black holes. This insight is vital for understanding the complex gravitational interactions that lead to black hole mergers. Studying the gravitational waves from black hole mergers helps to map the population of black holes in the universe. Each detected merger provides data on the number and distribution of black holes, helping to build a statistical picture of their prevalence and characteristics across different cosmic environments. Gravitational waves offer a unique test of general relativity in the strong field regime. The extreme gravitational conditions near merging black holes provide an opportunity to test Einstein's theory, in ways that are not possible with weaker gravitational fields. So far, the observations have been consistent with general relativity, but future detections might reveal deviations. Detecting gravitational waves from black holes also helps to understand their formation mechanisms. By comparing the properties of observed black hole mergers with theoretical models, scientists can infer whether the black holes formed from the collapse of massive stars, the merger of smaller black holes, or other processes. Gravitational waves provide insights into the environments where black hole mergers occur. For instance, the presence of certain features in the gravitational wave signal can indicate whether the merger happened in a dense star cluster or a galactic nucleus. This information helps to piece together the history and context of black hole formation. The precise timing of gravitational wave signals allows for accurate measurements of distances to black hole mergers. This capability is essential for cosmology, as it provides an independent method to measure the expansion rate of the universe, known as the Hubble constant. Observations of black hole mergers through gravitational waves can reveal the presence of intermediate mass black holes. These black holes, with masses between stellar mass and supermassive black holes, are challenging to detect with electromagnetic observations alone. Gravitational waves offer a promising way to identify and study these elusive objects. The detection of gravitational waves from black hole mergers has led to the discovery of black holes with masses previously thought to be rare or impossible. These findings challenge existing models of stellar evolution and black hole formation, prompting revisions and new theories. Gravitational wave observations help to study the rate of black hole mergers over cosmic time. By analyzing the frequency of detected mergers, scientists can infer how the rate of these events has changed throughout the history of the universe, providing insights into the evolution of black hole populations. The detection of black hole mergers in different types of galaxies helps to understand the role of environment in black hole formation and growth. For instance, detecting mergers in dwarf galaxies or the outskirts of larger galaxies can provide clues about the influence of galactic environment on black hole dynamics. Gravitational waves can also detect the merger of black holes with neutron stars. These mixed mergers provide unique information about the properties of neutron stars and the extreme physics governing their behavior. Observing these events helps to bridge our understanding of black holes and neutron stars. The precise localization of gravitational wave sources, when combined with electromagnetic observations, enables multi-messenger astronomy. This approach allows for the study of black hole mergers in conjunction with other signals, such as gamma-ray bursts or optical counterparts, providing a more comprehensive view of these events. Future advancements in gravitational wave detection will continue to enhance our understanding of black holes. As detectors become more sensitive and new observatories come online, the frequency and quality of black hole merger detections will increase, offering deeper insights into the nature and behavior of black holes across the universe. The process leading to the collision of black holes begins with the formation of a binary system. This system typically consists of two massive stars orbiting each other. As these stars evolve, they undergo various stages of stellar evolution, including supernova explosions, eventually leaving behind two black holes. Over time, the black holes in a binary system lose energy through the emission of gravitational waves. This energy loss causes the black holes to spiral closer together. The rate at which they lose energy and move inward depends on their masses, separation distance, and orbital parameters. As the black holes draw closer, their orbital speed increases. This acceleration further enhances the emission of gravitational waves, creating a feedback loop that accelerates the inspiral process. The gravitational waves produced during this phase are weaker, but increase in strength as the black holes approach each other. The inspiral phase can last for millions to billions of years, depending on the initial conditions of the binary system. Throughout this time, the black holes gradually move closer, emitting gravitational waves that carry away angular momentum and energy. This process tightens their orbit until they reach the final stages of inspiral. When the black holes are close enough, they enter the final few orbits before collision. During these last orbits, the emission of gravitational waves becomes extremely strong. The frequency and amplitude of these waves increase significantly, making them detectable by gravitational wave observatories on Earth. The last few milliseconds before the collision are the most energetic. The black holes move at a significant fraction of the speed of light, and the gravitational waves reach their peak strength. This phase, known as the merger phase, is when the black holes finally collide and merge into a single, more massive black hole. Upon merging, the newly formed black hole undergoes a period of ringdown. During this phase, the black hole settles into a stable state, emitting gravitational waves that gradually decrease in amplitude. These ringdown waves are the final signals that can be detected before the black hole becomes quiescent. The entire process, from the final in-spiral to the merger and ringdown, produces a distinct gravitational wave signal. This signal contains detailed information about the masses, spins, and other properties of the black holes involved. Analyzing this signal allows scientists to reconstruct the events leading to the collision. In some cases, the environment around the black holes can influence the collision process. For example, if the binary system is located in a dense star cluster, interactions with other stars can alter the black hole's orbits and affect the timing of the merger. Additionally, the presence of gas and dust can impact the dynamics of the in-spiral. The collision of black holes is not only a spectacular event, but also a source of valuable astrophysical data. The gravitational waves produced provide a direct way to study the properties of black holes and the nature of gravity in extreme conditions. Each detected collision helps to refine our understanding of these fundamental processes. Simulations play a crucial role in modeling the collision process. Numerical relativity simulations use powerful computers to solve Einstein's equations and predict the gravitational wave signals from merging black holes. These simulations help scientists interpret the observed signals and understand the physics of the merger. Observations of black hole collisions also provide insights into the formation and evolution of binary black hole systems. By studying the characteristics of the merging black holes, researchers can infer the origins and evolutionary paths of these systems, shedding light on the life cycles of massive stars. The study of black hole collisions is a rapidly advancing field, driven by technological improvements in gravitational wave detection. As detectors become more sensitive, the number of observed black hole mergers is expected to increase, providing a wealth of data for astrophysical research. Future observations and theoretical developments will continue to enhance our understanding of the collision process. With each new detection, scientists gain a deeper appreciation of the complexities and dynamics of black hole mergers, contributing to the broader knowledge of the universe's most extreme phenomena. The orbital dynamics of binary black holes are governed by the interplay of their gravitational attraction and the emission of gravitational waves. These dynamics are crucial for understanding the in-spiral and eventual merger of the black holes. In a binary black hole system, the two black holes orbit their common center of mass. The gravitational force between them dictates the shape and size of their orbit. Depending on their initial conditions, the orbit can be circular or elliptical. As the black holes orbit each other, they lose energy through the emission of gravitational waves. This energy loss causes the orbit to shrink and the black holes to move closer together. Over time, the orbit becomes more circular, even if it started out elliptical. The rate of orbital decay depends on the masses of the black holes and their separation. More massive black holes and closer separations result in stronger gravitational wave emission and faster in-spiral. This process can take millions or even billions of years, depending on the initial separation. The in-spiral phase is characterized by gradually increasing orbital speed and gravitational wave emission. As the black holes draw closer, their orbital period shortens, and they emit gravitational waves with higher frequency and amplitude. This increase continues until the black holes are very close to each other. During the final stages of in-spiral, the orbital speed of the black holes can reach significant fractions of the speed of light. The gravitational waves emitted during this phase are strong enough to be detected by observatories like LIGO and Virgo. The frequency and amplitude of these waves provide detailed information about the black hole's properties. The dynamics of the binary system are also influenced by the spins of the black holes. If the black holes have significant spin, their angular momenta can affect the orbital dynamics. The spins can cause the orbit to precess, meaning that the orientation of the orbit changes over time. When the black holes are very close to each other, they enter the merger phase. In this phase, the black hole's horizons begin to distort and eventually touch, leading to the formation of a single, more massive black hole. This merger produces a burst of gravitational waves, with a characteristic waveform. After the merger, the newly formed black hole undergoes a ringdown phase. During this phase, the black hole settles into a stable state, emitting gravitational waves that decrease in amplitude. This process is similar to how a struck bell emits sound waves as it returns to rest. The study of orbital dynamics in binary black hole systems helps scientists understand the conditions leading to black hole mergers. By analyzing the gravitational wave signals, researchers can infer the masses, spins, and other properties of the black holes, as well as the characteristics of their orbit. Numerical simulations are essential for modeling the complex dynamics of binary black holes. These simulations solve Einstein's equations for the two-body problem, predicting the gravitational waveforms that detectors might observe. Comparing these predictions with actual observations helps to validate the models and refine our understanding. The interaction between binary black holes and their surrounding environment can also affect their orbital dynamics. For instance, if the binary is in a dense stellar cluster or a gas-rich environment, interactions with other stars or gas can influence the orbit and potentially accelerate the inspiral. Gravitational wave observations have provided direct evidence of the orbital dynamics of binary black holes. Each detected merger event adds to the growing catalogue of observed systems, offering insights into the diversity and distribution of binary black holes in the universe. Understanding the orbital dynamics of binary black holes is not only important for astrophysics, but also for testing fundamental theories of gravity. These systems provide a natural laboratory for studying general relativity in the strong field regime, where the effects of gravity are extreme. Future observations and theoretical advancements will continue to shed light on the intricate dance of binary black holes. As our detection capabilities improve, we will uncover more about the nature of these fascinating systems and the forces that govern their evolution and eventual collision. The collision of black holes is an immensely energetic event, releasing a tremendous amount of energy in the form of gravitational waves. When two black holes spiral towards each other and merge, the energy emitted is so vast that it can outshine all the stars in the observable universe combined, but only for a brief moment. Gravitational waves carry this energy away from the merging black holes. Unlike electromagnetic waves, gravitational waves are ripples in the fabric of space-time itself. These waves travel at the speed of light, radiating outwards from the collision event. During the final stages of inspiral, the black holes emit increasingly powerful gravitational waves. As they get closer, their orbital velocities increase, and the frequency and amplitude of the waves rise sharply. This phase of rapid energy emission is known as the chirp, which is characterized by a distinctive increase in pitch. The peak energy emission occurs at the moment of merger, when the two black holes collide and form a single, more massive black hole. This collision produces a burst of gravitational waves that carry away a significant portion of the system's total mass energy. For stellar mass black holes, this energy can be equivalent to several solar masses converted directly into gravitational waves. After the merger, the newly formed black hole undergoes a ring-down phase. During this phase, the black hole settles into a stable state, emitting gravitational waves at specific frequencies that correspond to its vibrational modes. This process resembles how a struck bell emits sound waves as it returns to rest. The amount of energy emitted in gravitational waves depends on the masses and spins of the merging black holes. More massive black holes and those with higher spins tend to emit more energy. The precise characteristics of the emitted waves provide valuable information about the properties of the black holes involved. Gravitational wave detectors like LIGO and Virgo are designed to measure these tiny ripples in space-time. The detection of these waves allows scientists to estimate the energy released during the collision and gain insights into the dynamics of the merging black holes. The energy emitted during black hole collisions also has implications for our understanding of the universe's energy budget. These events convert a substantial amount of mass into gravitational radiation, highlighting the role of black hole mergers as significant sources of energy in the cosmos. The efficiency of energy conversion during black hole mergers is extraordinarily high. Unlike other astrophysical processes, where only a fraction of the available energy is released, black hole collisions can convert a large percentage of the system's mass into gravitational waves. Studying the energy emission from black hole collisions helps to test the predictions of general relativity. The observed waveforms can be compared with theoretical models to check for consistency and to look for any deviations that might suggest new physics. In addition to gravitational waves, black hole collisions can sometimes produce electromagnetic radiation if there is surrounding matter. For example, if the black holes are in a gas-rich environment, the interaction with this gas can create light, X-rays, or other forms of radiation, providing a multi-messenger signal. Multi-messenger observations, which combine gravitational wave data with electromagnetic signals, offer a more comprehensive view of black hole collisions. These combined observations can reveal details about the environment around the merging black holes and the mechanisms of energy release. The study of energy emission during black hole collisions also contributes to our understanding of black hole growth and the dynamics of binary systems. By analyzing the energy and waveforms, scientists can infer the history and evolution of the black holes prior to their merger. Future advancements in gravitational wave detection will enhance our ability to measure the energy emitted during black hole collisions with greater precision. As more detectors come online and existing ones improve in sensitivity, the frequency and quality of detected events will increase. Continued research into the energy emission of black hole collisions will deepen our understanding of these extraordinary events. Each new detection adds to our knowledge, helping to unravel the complexities of black hole dynamics and the fundamental nature of gravity. The spin and mass of black holes play critical roles in their collisions. These properties influence the dynamics of the inspiral, the waveform of the emitted gravitational waves, and the characteristics of the final merged black hole. Mass determines the gravitational pull between the black holes. More massive black holes exert stronger gravitational forces, causing them to spiral together more quickly. The total mass of the system affects the amplitude of the gravitational waves, with larger masses producing stronger signals. Spin, or the angular momentum of a black hole, significantly impacts the collision process. Black holes can spin at various rates, from 0 to near the speed of light. The spin affects the shape of the event horizon and the structure of the spacetime around the black hole. When both black holes in a binary system have significant spin, their interactions become more complex. The spins can be aligned or misaligned with the orbital plane. Aligned spins tend to simplify the inspiral, while misaligned spins can cause the orbit to precess, leading to more intricate gravitational waveforms. The combined effects of spin and mass determine the energy and angular momentum radiated away during the inspiral and merger. These factors influence the final spin and mass of the newly formed black hole. Understanding these dynamics is essential for interpreting gravitational wave data. The final spin of the merged black hole depends on the initial spins and masses of the progenitor black holes. High initial spins and certain mass ratios can result in a rapidly spinning final black hole. The spin affects the stability and future evolution of the merged black hole. The mass ratio of the binary system, defined as the ratio of the masses of the two black holes, influences the gravitational wave signal. Systems with nearly equal masses produce stronger, more easily detectable signals. In contrast, systems with very different masses produce weaker signals that are harder to detect. The spin of black holes also affects the merger's gravitational wave frequency. Faster spinning black holes shift the frequency of the emitted waves, which can be detected and analyzed by observatories. These frequency shifts provide insights into the spins of the merging black holes. During the merger, the interaction of the black hole's spins can produce unique gravitational wave signatures. For example, highly spinning black holes can create more pronounced and distinguishable wave patterns. These signatures help scientists determine the spin properties of the black holes involved. The spin-induced precession of the orbit during the inspiral phase can cause modulations in the gravitational wave signal. These modulations provide information about the orientation and magnitude of the spins, adding another layer of detail to the analysis of the merger event. The spins and masses also influence the kick velocity of the final black hole. After the merger, the newly formed black hole can receive a recoil or kick due to the asymmetrical emission of gravitational waves. The magnitude of this kick depends on the spins and masses of the merging black holes. High kick velocities can eject the newly formed black hole from its host galaxy. This phenomenon has implications for the retention and growth of black holes in different galactic environments. Studying these kicks helps to understand the distribution and population of black holes in the universe. The interaction between spin and mass during collisions can also affect the surrounding environment. In gas-rich environments, the dynamics of the merger can influence the behavior of the gas, potentially leading to observable electromagnetic counterparts. These interactions provide additional observational opportunities. Gravitational wave observations of black hole collisions with different spin and mass configurations help to test theories of black hole formation and evolution. By comparing observed data with theoretical models, scientists can refine their understanding of these processes and the physics governing black holes. Future gravitational wave detections and improvements in detector sensitivity will continue to reveal more about the roles of spin and mass in black hole collisions. Each new observation adds to the growing body of knowledge, enhancing our understanding of these extraordinary cosmic events and the fundamental nature of gravity. The final merger phase of black hole collisions is an intense and dramatic event. As the black holes draw extremely close, their gravitational fields distort significantly, and their horizons begin to merge. This phase emits the most powerful gravitational waves detected during the entire process. During the last orbits, the black holes move at incredible speeds, approaching a significant fraction of the speed of light. The gravitational waves produced at this stage are at their peak amplitude and frequency, creating a distinctive waveform known as the chirp. The merger itself happens quickly in a matter of milliseconds. As the black holes collide, their horizons touch and merge, forming a single, larger black hole. This newly formed black hole is initially in a highly excited state, characterized by violent oscillations. These oscillations are part of the ring-down phase, where the merged black hole emits gravitational waves as it settles into a stable configuration. The gravitational waves produced during ring-down are less intense, but provide crucial information about the final black hole's properties. The ring-down waveform is determined by the mass and spin of the new black hole. By analyzing this waveform, scientists can infer these properties with high precision. The ring-down phase is akin to the dying tones of a ringing bell, gradually diminishing as the black hole stabilizes. The energy released during the merger is enormous, with a portion of the combined mass of the black holes being converted into gravitational waves. This energy release can be several times the mass of the Sun, making it one of the most energetic events in the universe. The final spin of the black hole formed in the merger depends on the initial spins and mass ratio of the colliding black holes. High spins can lead to a rapidly rotating final black hole, which affects its subsequent evolution and interactions with its environment. The merged black hole may receive a recoil kick due to the asymmetrical emission of gravitational waves. This kick can impart a velocity to the black hole, potentially ejecting it from its host galaxy if the velocity is high enough. The magnitude of the kick is influenced by the spins and mass ratio of the merging black holes. The dynamics of the final merger phase are highly complex and are studied using numerical relativity simulations. These simulations solve Einstein's equations for the two-body problem, providing detailed predictions of the gravitational wave signals that are compared with actual observations. Gravitational wave observatories like LIGO and Virgo capture the signals from the final merger phase with remarkable precision. These signals provide a wealth of information about the black hole's masses, spins, and the dynamics of the merger, contributing to our understanding of black hole physics. The detection of gravitational waves from the final merger phase has confirmed many aspects of general relativity, particularly in the strong field regime. These observations offer direct evidence of the existence of black holes and the nature of their interactions, validating theoretical predictions. Multi-messenger observations, combining gravitational waves with electromagnetic signals, can provide a more comprehensive picture of the final merger phase. In some cases, if the black holes are surrounded by matter, the merger may produce electromagnetic counterparts such as gamma-ray bursts or afterglows. The final merger phase is not only a spectacular event, but also a window into the most extreme gravitational interactions in the universe. Each detected merger adds to our knowledge of black hole demographics, their formation channels, and the conditions leading to their collisions. As gravitational wave detectors become more sensitive, we expect to observe a greater variety of black hole mergers. This will allow scientists to study the final merger phase in different contexts, including mergers involving black holes with extreme spins or in unique astrophysical environments. The study of the final merger phase is crucial for advancing our understanding of fundamental physics, including the behavior of gravity under extreme conditions. Continued research and future observations will deepen our insights into these extraordinary cosmic events and the fundamental laws governing our universe. Major observatories and instruments play a pivotal role in the detection and study of gravitational waves. LIGO, the Laser Interferometer. Gravitational Wave Observatory is one of the most prominent. With 2 facilities in the United States, LIGO uses laser interferometry to detect minute distortions in space-time caused by passing gravitational waves. Virgo, located in Italy, complements LIGO by providing additional data and enhancing the ability to triangulate the source of gravitational waves. Virgo's design and technology are similar to LIGO's, but its collaboration with LIGO improves the precision and accuracy of detections. CAGRA, situated in Japan, adds a unique dimension to the global network of gravitational wave detectors. Built underground to reduce seismic noise, CAGRA also employs cryogenic mirrors to minimize thermal noise, contributing to more sensitive measurements. LISA, the Laser Interferometer Space Antenna, represents the future of gravitational wave astronomy. Planned as a space-based observatory, LISA will consist of 3 spacecraft forming a large triangular interferometer. This configuration will allow LISA to detect low-frequency gravitational waves, such as those from supermassive black hole mergers. The Einstein telescope is another upcoming project designed to enhance gravitational wave detection. This next-generation ground-based observatory will feature longer arms and improved technology, aiming to increase sensitivity and detect a broader range of gravitational wave sources. Pulsar timing arrays, PTAs, are an innovative method for detecting gravitational waves. By monitoring the precise timing of pulsars, these arrays can detect the influence of gravitational waves passing through our galaxy. PTAs are sensitive to very low-frequency gravitational waves. The North American Nanohertz Observatory for Gravitational Waves, NanoGrav, is a leading PTA project. By tracking millisecond pulsars, NanoGrav aims to detect gravitational waves from sources such as supermassive black hole binaries and cosmic strings. The European Pulsar Timing Array, EPTA, and the Parkes Pulsar Timing Array, PPTA, in Australia also contribute to this effort. These collaborations enhance global coverage and increase the likelihood of detecting gravitational waves through pulsar timing. The Event Horizon Telescope, EHT, is notable for capturing the first image of a black hole's event horizon. Although not a gravitational wave detector, EHT provides complementary data by observing the environments around supermassive black holes, enhancing our understanding of black hole physics. Advanced LIGO and Advanced Virgo represent significant upgrades to the original detectors, featuring improved sensitivity and noise reduction techniques. These enhancements have increased the number of detected gravitational wave events and the accuracy of measurements. Ground-based detectors like LIGO and Virgo are limited by seismic and thermal noise. To overcome these challenges, researchers continually develop new technologies, such as improved mirror coatings and more sophisticated vibration isolation systems. The global network of gravitational wave detectors relies on international collaboration. Data sharing and joint analysis efforts enhance the ability to detect and accurately locate gravitational wave sources, providing a more comprehensive understanding of these events. Technological advancements in quantum sensing and optics are pushing the boundaries of gravitational wave detection. Innovations like quantum squeezing reduce quantum noise, allowing detectors to measure weaker signals with greater precision. Gravitational wave detectors also benefit from advances in computing and data analysis. High-performance computing systems process the vast amounts of data generated by these observatories, employing complex algorithms to identify potential gravitational wave signals amidst noise. The synergy between different types of observatories, including gravitational wave detectors, electromagnetic telescopes, and neutrino observatories, fosters a multi-messenger approach to astronomy. This holistic view enables scientists to study cosmic events from multiple perspectives, leading to a richer and more detailed understanding of the universe. The collaboration between LIGO and Virgo has significantly advanced the field of gravitational wave astronomy. By working together, these observatories can more accurately detect and analyze gravitational wave signals from cosmic events such as black hole and neutron star mergers. LIGO, with its 2 detectors in the United States, provides extensive coverage and sensitivity. Virgo, located in Italy, adds a crucial third detector to the network, improving the ability to triangulate the source of gravitational waves and pinpoint their origin in the sky. The joint efforts of LIGO and Virgo allow for more precise localization of gravitational wave sources. With 3 detectors, the network can better determine the direction from which the waves are coming, making it easier to identify and study the source. Collaboration enhances the sensitivity of the detectors. By combining data from LIGO and Virgo, scientists can filter out noise more effectively and identify weaker gravitational wave signals that might be missed by a single observatory. The partnership between LIGO and Virgo also enables rapid sharing of data and alerts. When a gravitational wave event is detected, an alert is sent out to the global scientific community. This prompt notification allows other telescopes and observatories to follow up and search for electromagnetic counterparts. One of the most significant outcomes of the LIGO-Virgo collaboration was the detection of GW170817, a gravitational wave signal from a neutron star merger. This event was also observed across the electromagnetic spectrum, marking the first instance of multi-messenger astronomy and providing valuable insights into the origin of heavy elements. The collaboration has led to the discovery of dozens of gravitational wave events, including numerous black hole mergers. Each detection adds to our understanding of these phenomena and helps to refine models of stellar evolution and black hole formation. Joint efforts have also improved the calibration and accuracy of gravitational wave measurements. By cross-checking data and methodologies, LIGO and Virgo can ensure that their findings are robust and reliable, enhancing the credibility of their scientific results. LIGO and Virgo's collaborative approach extends to data analysis. Teams from both observatories work together to develop and implement sophisticated algorithms that can sift through vast amounts of data to identify potential gravitational wave signals. The collaboration has fostered an international scientific community dedicated to gravitational wave research. Conferences, workshops, and collaborative projects bring together researchers from around the world, facilitating the exchange of ideas and advancements in the field. LIGO and Virgo also engage in joint public outreach and education efforts. By sharing their discoveries and the excitement of gravitational wave astronomy with the public, they help to inspire the next generation of scientists and raise awareness about the importance of this research. The success of the LIGO-Virgo collaboration has paved the way for the inclusion of additional observatories, such as Kagra in Japan. As more detectors join the network, the ability to detect and study gravitational waves will continue to improve, leading to even more discoveries. The collaborative framework developed by LIGO and Virgo serves as a model for future scientific endeavors. By pooling resources and expertise, scientists can tackle complex problems and achieve breakthroughs that would be impossible for individual institutions working alone. The ongoing collaboration between LIGO and Virgo promises to unlock further mysteries of the universe. With each new detection, we gain a deeper understanding of gravitational waves and the cataclysmic events that produce them, contributing to a more comprehensive picture of the cosmos. As the field of gravitational wave astronomy evolves, the partnership between LIGO and Virgo will remain a cornerstone of research efforts. Together, they will continue to explore the universe, pushing the boundaries of our knowledge and revealing the hidden dynamics of the most extreme events in space. One of the most significant observed collisions is GW150914, the first direct detection of gravitational waves. This event involved the merger of 2 black holes, each around 30 times the mass of the Sun, located about 1.3 billion light-years away. It marked the beginning of gravitational wave astronomy. Another notable event is GW170104, detected in January 2017. This collision involved 2 black holes with masses of about 31 and 19 solar masses, merging approximately 3 billion light-years away. The observation helped confirm that black hole mergers are common throughout the universe. GW170814 was a groundbreaking detection, as it was the first event observed by the LIGO and Virgo detectors together. This event involved black holes with masses of about 30 and 25 solar masses, merging around 1.8 billion light-years away. The addition of Virgo improved the localization of the source. GW170817 stands out as a landmark in multi-messenger astronomy. This event was the merger of 2 neutron stars, observed both in gravitational waves and across the electromagnetic spectrum. The collision produced heavy elements like gold and platinum, and provided insights into the origin of these elements in the universe. GW 190521, detected in May 2019, was notable for involving the most massive black holes observed to date through gravitational waves. The black holes had masses of about 85 and 66 solar masses. The merger resulted in a final black hole of about 142 solar masses, providing the first direct observation of an intermediate mass black hole. GW 190425 was another significant neutron star merger observed in April 2019. This event involved two neutron stars with a combined mass greater than any previously known neutron star binary system, shedding light on the diversity of neutron star mergers and their role in the universe. GW 190412 provided new insights into the spin and mass ratio of merging black holes. Detected in April 2019, this event involved black holes with masses of about 30 and 8 solar masses. The unequal mass ratio and the high spin of the smaller black hole offered valuable data for theoretical models. GW 190814, detected in August 2019, was remarkable due to its asymmetric mass ratio. The merger involved a black hole about 23 times the mass of the Sun and a compact object about 2.6 times the mass of the Sun. The nature of the smaller object, whether it was a neutron star or a light black hole, remains a topic of investigation. GW 1151226 was the second confirmed detection of gravitational waves, observed in December 2015. This event involved the merger of two black holes with masses of about 14 and 8 solar masses, located 1.4 billion light-years away. It confirmed the robustness of LIGO's detection capabilities. GW 170608, detected in June 2017, involved black holes with masses of about 12 and 7 solar masses. The relatively low mass of these black holes provided a different perspective on the population of merging black holes and their formation scenarios. GW 190521G, although not as massive as other observed events, was significant for its possible association with a gamma-ray burst detected by the Fermi Gamma-Ray Space Telescope. This potential link between gravitational waves and electromagnetic radiation continues to be a focus of research. GW 190426 Folfin 2155 was a candidate event involving a possible neutron star black hole merger. Although the exact nature of the merger remains uncertain, it highlights the ongoing efforts to understand the full range of compact object interactions observable through gravitational waves. GW 19905177055101 was another intriguing event, detected in May 2019. The merger involved black holes with masses around 35 and 24 solar masses. The event contributed to the growing catalogue of black hole mergers and the diversity of their properties. GW 170104 provided insights into the spin alignment of merging black holes. The detection indicated that the black hole's spins were likely misaligned with their orbital plane, suggesting complex formation histories and dynamics within their binary system. The detection of GW 19700823, observed in August 2017, added to the understanding of black hole populations. Involving black holes with masses of about 39 and 29 solar masses, the event took place around 3 billion light-years away and reinforced the evidence that black hole mergers occur frequently in the distant universe. Data analysis and interpretation are crucial components of gravitational wave astronomy. When a potential gravitational wave signal is detected, it is initially identified by automated algorithms that sift through the vast amounts of data collected by observatories like LIGO and Virgo. These algorithms are designed to distinguish genuine signals from background noise. They use techniques such as matched filtering, which compares the data against a library of theoretical waveforms predicted by models of black hole and neutron star mergers. Once a candidate signal is identified, it undergoes further scrutiny by scientists. They perform a detailed analysis to confirm the signal's authenticity, checking for consistency across multiple detectors, and ensuring it is not an artifact of instrumental noise or other interference. Key parameters such as the masses, spins, and distance of the merging objects are extracted from the signal. This involves fitting the observed waveform to theoretical models, which describe how the gravitational wave signal evolves over time during the in-spiral merger and ring-down phases. The analysis also includes estimating the sky location of the source. By comparing the arrival times of the signal at different detectors, scientists can triangulate the position of the source in the sky, narrowing down the region where the event occurred. Advanced statistical techniques are employed to assess the significance of the detection. This involves calculating the false alarm rate, which is the probability that a similar signal could be produced by random noise. A low false alarm rate indicates a high confidence detection. Interpreting the data provides insights into the astrophysical processes behind the detected events. For example, the mass and spin measurements can reveal information about the formation history of the black holes or neutron stars involved, such as whether they were formed in isolation or through dynamical interactions in dense star clusters. The data also offer tests of general relativity in the strong field regime. By comparing the observed waveforms to predictions made by Einstein's theory, scientists can look for any deviations that might suggest new physics or modifications to our understanding of gravity. Gravitational wave signals can be combined with electromagnetic observations to provide a more comprehensive picture of the events. For instance, detecting a gamma-ray burst or optical counterpart alongside a gravitational wave signal can help identify the precise nature of the source and its environment. Data from multiple gravitational wave detections are combined to build a statistical picture of the population of merging black holes and neutron stars. This helps to estimate the rates of these events across the universe and to understand their contribution to the overall gravitational wave background. The analysis process is iterative and involves continuous refinement. As new detections are made and more data are collected, scientists update their models and improve the accuracy of their parameter estimates, leading to a deeper understanding of the observed phenomena. International collaboration plays a key role in data analysis. Scientists from around the world work together to share methods, tools, and results, enhancing the robustness and reliability of the findings. This collaborative approach accelerates the pace of discovery and innovation in gravitational wave astronomy. Public data releases are an important aspect of the field. LIGO and Virgo periodically release data from their observing runs, allowing the broader scientific community and citizen scientists to contribute to the analysis and interpretation of gravitational wave signals. Machine learning and artificial intelligence are increasingly being used to improve data analysis techniques. These technologies help to automate the detection process, identify patterns in the data, and enhance the sensitivity of gravitational wave searches. The insights gained from data analysis and interpretation not only advance our understanding of black holes and neutron stars, but also have broader implications for astrophysics and cosmology. Each detection provides a new piece of the puzzle, helping to unravel the mysteries of the universe. Gravitational waves provide profound insights into general relativity, testing its predictions in the most extreme environments. By observing black hole mergers, scientists can directly test the theory's accuracy under conditions of intense gravitational fields and high velocities. One key prediction of general relativity is the existence of gravitational waves themselves. The detection of these waves by LIGO and Virgo has confirmed this aspect of Einstein's theory, providing direct evidence of space-time ripples caused by accelerating masses. The waveforms of detected gravitational waves match the predictions made by general relativity with remarkable precision. These waveforms describe how the signal changes over time, reflecting the in-spiral merger and ring-down phases of black hole collisions. General relativity predicts the speed at which gravitational waves travel. Observations confirm that they propagate at the speed of light, consistent with the theory's assertion that gravitational waves are disturbances in the fabric of space-time. The observation of gravitational waves from multiple black hole mergers allows for stringent tests of general relativity. Any deviations from the predicted waveforms could indicate new physics or the need for modifications to the theory. The no-hair theorem is a key aspect of general relativity, stating that black holes can be fully described by just three parameters: mass, spin, and charge. Gravitational wave observations help verify this theorem by providing detailed measurements of these parameters. Gravitational wave data also test the strong equivalence principle, which asserts that the laws of gravity are the same in all reference frames. The consistency of gravitational wave signals across different detectors supports this principle, reinforcing the validity of general relativity. The merger phase of black holes, characterized by extreme gravitational interactions, offers unique opportunities to test the limits of general relativity. The precise match between observed and predicted waveforms during this phase provides strong evidence for the theory's robustness. Ring-down signals, the gravitational waves emitted as a newly formed black hole settles into a stable state, offer additional tests of general relativity. The frequencies and damping times of these signals match the theoretical predictions, confirming the theory's accuracy in describing black hole dynamics. Gravitational wave observations can also constrain alternative theories of gravity. By comparing the detected signals with predictions from other theories, scientists can rule out or place limits on models that deviate from general relativity. Black hole spin measurements derived from gravitational wave data test predictions about the alignment and distribution of spins in merging systems. These measurements help to understand whether black holes are born with high spins or acquire them through accretion and mergers, providing insights into their formation and evolution. Gravitational wave observations of neutron star mergers test general relativity in the presence of extreme densities and nuclear interactions. These events offer a different regime for testing the theory, complementing black hole observations and providing a broader validation of general relativity. The detection of gravitational waves from binary neutron star mergers, like GW170817, allows for tests of the speed of gravitational waves relative to the speed of light. The simultaneous observation of gravitational waves and electromagnetic signals confirms that they travel at the same speed, consistent with general relativity. The precise timing of gravitational wave signals helps to test the invariance of the speed of light and the nature of space-time itself. By measuring the arrival times of waves from distant sources, scientists can probe fundamental aspects of the universe's structure predicted by general relativity. Future gravitational wave observations, especially with more sensitive detectors and a broader range of detected events, will continue to test and refine general relativity. Each new detection offers an opportunity to explore the theory's predictions and search for potential signs of new physics, deepening our understanding of the universe. Testing predictions of Einstein's theory of general relativity is one of the primary goals of gravitational wave astronomy. Gravitational waves offer a unique opportunity to test these predictions in extreme conditions that are not accessible by any other means. The detection of gravitational waves itself is a direct confirmation of one of Einstein's predictions. The existence of these waves, ripples in the fabric of space-time caused by accelerating massive objects, was a fundamental aspect of general relativity that had eluded direct detection until recently. Gravitational waveforms predicted by general relativity describe the signal emitted by binary systems of black holes or neutron stars. The precise match between observed waveforms and theoretical predictions from general relativity confirms the theory's accuracy in describing the inspiral, merger, and ring-down phases of these collisions. General relativity predicts that gravitational waves should travel at the speed of light. Observations from events like GW170817, where gravitational waves and electromagnetic signals were detected simultaneously, have confirmed that they do indeed travel at this speed, validating Einstein's theory. The theory also predicts the no-hair theorem for black holes, which states that black holes can be fully described by their mass, spin, and charge. Gravitational wave data from black hole mergers help to confirm this theorem by providing precise measurements of these parameters. Einstein's theory includes the prediction that gravitational waves carry energy away from their sources, causing binary systems to lose energy and inspiral over time. Observations of binary pulsar systems, such as the Hulse-Taylor binary, and the direct detection of gravitational waves from black hole mergers provide strong evidence for this energy loss mechanism. The strong equivalence principle, another cornerstone of general relativity, asserts that gravitational motion is independent of the internal structure and composition of objects. Gravitational wave observations confirm this principle by showing consistent waveforms regardless of the properties of the merging black holes or neutron stars. Frame dragging, an effect predicted by general relativity, occurs when a massive rotating object drags space-time around with it. The spins of black holes measured through gravitational wave observations provide evidence for this effect, especially in systems where the black holes have significant spin. The inspiral and merger of binary black holes provide a natural laboratory for testing general relativity in the strong field regime. The gravitational waves emitted during these events come from regions of extremely curved spacetime, allowing scientists to test the theory under conditions that are far more extreme than those found near Earth. Gravitational wave observations also help to test the predictions of the ring-down phase, where the newly formed black hole emits gravitational waves as it settles into a stable state. The frequencies and decay times of these ring-down waves match the predictions of general relativity, confirming the theory's accuracy in describing black hole dynamics. Another prediction of general relativity is the relationship between the masses and spins of merging black holes and the gravitational waves they emit. The observed distribution of these parameters in detected events provides a statistical test of the theory, confirming its predictions across a range of systems. Gravitational waves allow scientists to test the prediction that the gravitational interaction is mediated by a massless spin-2 field. Deviations from the expected waveforms could indicate the presence of massive gravitons or other exotic particles, providing a test for modifications to general relativity. The detection of gravitational waves from neutron star mergers provides tests of general relativity in regimes where both gravitational and nuclear forces are important. These observations help to probe the equation of state of nuclear matter and the behavior of spacetime in the presence of extreme densities. Comparisons between gravitational wave observations and other tests of general relativity, such as the precise tracking of planetary orbits and time dilation measurements, provide a comprehensive picture of the theory's validity. These complementary tests strengthen the overall case for general relativity as the correct description of gravity. Future observations with more sensitive detectors and a broader range of gravitational wave sources will continue to test Einstein's predictions. Each new detection offers an opportunity to explore the theory's predictions in more detail and to search for potential deviations that could hint at new physics. The black hole information paradox is a fundamental problem in theoretical physics that arises from the nature of black holes and quantum mechanics. It questions what happens to information about the physical state of objects that fall into a black hole. According to general relativity, information about the matter that forms a black hole or falls into it is lost to the outside world. The black hole can be described entirely by its mass, spin, and charge, with no other details about the original matter being accessible. However, quantum mechanics suggests that information is never lost. This principle is known as unitarity, which implies that the complete description of a system state should allow for the recovery of all previous states. This creates a paradox when applied to black holes. The paradox was highlighted by Stephen Hawking's work in the 1970s. Hawking showed that black holes can emit radiation due to quantum effects near the event horizon, a phenomenon now known as Hawking radiation. This radiation causes black holes to lose mass and energy over time, potentially leading to their evaporation. Hawking's calculations suggested that the information about the matter inside a black hole could be permanently lost as the black hole evaporates. This conclusion conflicts with the principles of quantum mechanics, creating a significant puzzle for physicists. One proposed solution to the paradox is that information is somehow encoded in the Hawking radiation. This idea, known as the holographic principle, suggests that all the information contained in a three-dimensional volume can be represented on its two-dimensional boundary. The holographic principle is supported by the ADS-CFT correspondence, a theoretical framework that relates a gravity theory in a higher dimensional space to a quantum field theory on its boundary. This correspondence has provided insights into how information might be preserved in black hole evaporation. Another approach to resolving the paradox involves modifications to the event horizon. Some theories propose that the event horizon is not a smooth boundary, but has a complex structure, such as a firewall, which could potentially encode and release information. The concept of black hole complementarity also offers a possible resolution. This idea suggests that information is both reflected at the event horizon and passes through it, depending on the observer's perspective. This could reconcile the loss of information with quantum mechanics. Recent advances in theoretical physics, such as the study of quantum entanglement and entropy, have provided new tools for addressing the information paradox. These approaches explore how information can be distributed and preserved in the entangled states of particles. The paradox has led to the development of new ideas in quantum gravity, including string theory and loop quantum gravity. These theories attempt to unify general relativity and quantum mechanics, offering potential solutions to the information paradox. Experimental evidence is challenging to obtain, but gravitational wave observations of black holes could provide indirect insights. By studying the properties and behaviors of black holes, scientists hope to gather clues about the fundamental nature of information in these extreme environments. The black hole information paradox remains an active area of research, inspiring a wide range of theoretical developments. It challenges our understanding of space, time, and the fundamental laws of physics, driving the search for a deeper theory that unites gravity with quantum mechanics. Collaborative efforts among physicists from various disciplines are essential in tackling the paradox. By combining insights from quantum field theory, general relativity, and statistical mechanics, researchers aim to develop a coherent framework that resolves the paradox. Future breakthroughs in understanding black holes and the nature of information may not only solve the paradox but also provide profound insights into the workings of the universe. The resolution of this paradox is expected to have far-reaching implications for our understanding of fundamental physics. Quantum gravity theories aim to unify general relativity with quantum mechanics, addressing the fundamental nature of space-time at the smallest scales. One of the leading approaches is string theory, which proposes that the fundamental constituents of the universe are one-dimensional strings rather than point particles. String theory suggests that different modes of vibration of these strings correspond to different particles, including the graviton, which mediates the force of gravity. This framework naturally incorporates gravity into a quantum theory and provides a consistent description of all known particles and forces. Another prominent approach is loop quantum gravity, which focuses on quantizing space-time itself. In this theory, space-time is composed of discrete loops, or spin networks, that define the geometry at the Planck scale. This discretization leads to a finite and well-defined quantum theory of gravity. Loop quantum gravity predicts that space-time has a granular structure at the smallest scales, which could lead to observable effects such as discrete spectra for areas and volumes. These predictions offer potential experimental tests for the theory. The holographic principle, derived from string theory and black hole thermodynamics, also plays a crucial role in quantum gravity. It posits that all the information contained within a volume of space can be represented on its boundary, providing a new way to think about the nature of space-time and information. The ADS-CFT correspondence is a specific realization of the holographic principle. It relates a gravity theory in a higher dimensional anti-de Sitter ADS space to a conformal field theory, CFT, on its boundary. This duality has provided valuable insights into quantum gravity and strongly interacting quantum systems. Colossal dynamical triangulations, CDT, is another approach to quantum gravity. CDT constructs space-time from fundamental building blocks, or simplices, and evolves them according to specific rules that preserve causality. This method aims to recover a smooth classical space-time at large scales. Asymptotic safety is a framework that suggests gravity can be described by a quantum field theory that remains well-behaved at all energy scales. This approach involves finding a fixed point in the renormalization group flow, where the theory becomes scale-invariant and free from divergences. Non-commutative geometry introduces the idea that space-time coordinates do not commute, leading to a modified structure of space-time at small scales. This approach offers a potential way to incorporate quantum effects into the fabric of space-time. Hojava-Lifshitz gravity is a theory that modifies general relativity to become renormalizable by treating time and space differently at high energies. This anisotropic scaling leads to a theory that is well-defined at short distances and provides a potential candidate for quantum gravity. Twistor theory, introduced by Roger Penrose, represents space-time events as points in a complex space called twistor space. This approach offers an alternative way to describe the geometry of space-time and has connections to both general relativity and quantum field theory. Research in quantum gravity also explores the connections between gravity and thermodynamics. The study of black hole entropy and the nature of space-time horizons has revealed deep links between gravitational dynamics and thermodynamic laws, suggesting that space-time itself may have an underlying statistical description. The search for a quantum theory of gravity involves both theoretical advancements and potential experimental tests. High-energy particle collisions, cosmological observations, and precision measurements of gravitational waves may provide clues about the quantum nature of gravity. The resolution of the black hole information paradox is expected to play a key role in the development of quantum gravity theories. Understanding how information is preserved in black hole evaporation could reveal fundamental aspects of space-time and quantum mechanics. Quantum gravity remains one of the most challenging and exciting areas of theoretical physics. As research progresses, new ideas and insights will continue to emerge, bringing us closer to a unified understanding of the fundamental forces and the nature of the universe. Gravitational wave observations have profound impacts on cosmology and our understanding of the universe's evolution. By detecting these waves, we gain direct insights into some of the most violent and energetic events in the cosmos, such as black hole mergers and neutron star collisions. One major impact is on our understanding of the early universe. Gravitational waves produced during the inflationary period shortly after the Big Bang could provide clues about the conditions and processes that shaped the cosmos. Detecting these primordial waves would offer a unique glimpse into the universe's infancy. Gravitational waves also help to refine measurements of the Hubble constant, which describes the rate of the universe's expansion. By observing gravitational wave events and their electromagnetic counterparts, scientists can use these standard sirens to calculate distances and improve our understanding of cosmic expansion. The study of black hole and neutron star populations through gravitational wave observations contributes to our knowledge of stellar evolution and the life cycle of stars. By understanding how these compact objects form, merge, and interact, we can piece together a more complete picture of galaxy formation and evolution. Gravitational waves provide evidence for the existence of intermediate mass black holes, which fill the gap between stellar mass and supermassive black holes. Observing these elusive objects helps to explain their role in the growth of supermassive black holes and the dynamics of galaxies. The detection of binary neutron star mergers, such as GW70817, has significant implications for nuclear synthesis, the process by which heavy elements are formed. These events produce elements like gold and platinum, enriching the universe with the building blocks for planets and life. Gravitational wave astronomy enhances our understanding of dark matter. While gravitational waves are not directly affected by dark matter, their interactions with visible matter during cosmic events can provide indirect clues about the nature and distribution of dark matter in the universe. The observation of gravitational waves from black hole mergers helps to test and refine models of galaxy mergers and interactions. These events are key drivers of galactic evolution, influencing star formation rates, the distribution of matter, and the growth of central black holes. Gravitational waves allow us to probe the universe at different scales and epochs, from the local universe to the most distant reaches. This multi-scale observation capability provides a comprehensive view of the cosmos, revealing how structures form and evolve over time. The study of gravitational waves contributes to our understanding of the large-scale structure of the universe. By mapping the locations and frequencies of detected events, scientists can explore the distribution of matter and the influence of gravity on cosmic scales. Gravitational wave observations have the potential to reveal new and unexpected phenomena. Each detection expands our knowledge and can lead to the discovery of exotic objects or processes that challenge existing theories and inspire new lines of inquiry. The integration of gravitational wave data with traditional astronomical observations creates a richer, more detailed picture of the universe. This multi-messenger approach combines different types of information, providing a deeper understanding of cosmic events and their impacts. Gravitational waves offer a unique way to test fundamental physics in regimes that are inaccessible by other means. By studying these waves, scientists can explore the behavior of gravity under extreme conditions, test the limits of general relativity, and search for signs of new physics. As gravitational wave detectors improve in sensitivity and new observatories come online, the frequency and variety of detected events will increase. This growing dataset will continue to refine our models of the universe's evolution and enhance our understanding of the fundamental forces at play. The ongoing study of gravitational waves is transforming cosmology and our comprehension of the universe. By revealing the hidden dynamics of the cosmos, gravitational waves are unlocking new chapters in the story of the universe, from its earliest moments to its ongoing evolution. Gravitational waves have captured the imagination of the public and have influenced popular culture and media in profound ways. The groundbreaking discoveries have been featured in numerous news articles, documentaries, and TV shows, making complex scientific concepts more accessible to a broader audience. The excitement surrounding the first detection of gravitational waves by LIGO in 2015 led to widespread media coverage. This historic event was reported globally, highlighting the significance of the discovery and the new era of gravitational wave astronomy. Gravitational waves have inspired numerous science fiction stories and films. The idea of ripples in spacetime and the merging of massive cosmic objects provides fertile ground for imaginative storytelling, blending scientific fact with creative speculation. Movies such as Interstellar have incorporated elements of gravitational wave science into their plots. The film consulted with physicist Kip Thorne, ensuring that its depiction of black holes and spacetime was grounded in real scientific principles, further popularizing these concepts. Documentaries on platforms like Netflix and the Discovery Channel have explored the topic of gravitational waves, featuring interviews with leading scientists and detailed explanations of the technology and theories behind the detections. These programs help to demystify the science and engage viewers. Gravitational wave discoveries have been celebrated in public lectures and science festivals. Prominent scientists often give talks that explain the significance of these waves and their impact on our understanding of the universe, reaching audiences of all ages and backgrounds. The excitement around gravitational waves has also been reflected in social media. Platforms like Twitter, Facebook, and Instagram have seen numerous posts and discussions about the latest discoveries, often using visualizations and animations to illustrate how gravitational waves work. Educational institutions have incorporated gravitational wave science into their curricula. Schools and universities use the discoveries as case studies in physics and astronomy courses, inspiring students to pursue careers in science and fostering a new generation of researchers. Popular science books have delved into the topic of gravitational waves, making the science accessible to general readers. Authors like Janna Levin and Brian Greene have written engaging narratives that explain the history, science, and implications of these discoveries. Art and music have also been influenced by gravitational waves. Some artists have created visual art inspired by the concept of ripples in space-time, while musicians have used data from gravitational wave detections to create compositions that sonify the waves. Gravitational wave discoveries have been featured in various science magazines and journals, with cover stories and in-depth articles that explore the implications of these findings for our understanding of the cosmos. These publications help to maintain public interest and support for scientific research. Podcasts dedicated to science and astronomy frequently discuss gravitational wave discoveries, bringing expert interviews and detailed analyses to listeners. These podcasts offer an intimate and engaging way to learn about the latest developments in the field. Public interest in gravitational waves has led to increased funding and support for scientific research. The excitement generated by these discoveries has helped to secure investments in new detectors and technology, ensuring that the study of gravitational waves will continue to advance. Gravitational wave science has become a symbol of human curiosity and the quest for knowledge. The ability to detect and study these waves is seen as a testament to human ingenuity and the power of collaboration, inspiring a sense of wonder and possibility. The influence of gravitational waves on popular culture and media underscores the importance of scientific communication. By effectively sharing the excitement and significance of these discoveries, scientists can engage the public and foster a deeper appreciation for the mysteries of the universe. Gravitational wave discoveries have made significant contributions to STEM education by providing real-world examples of cutting-edge science. These discoveries have been incorporated into curricula at all educational levels, from elementary schools to universities. Teachers use gravitational wave detections as case studies to illustrate fundamental principles of physics, such as general relativity, wave propagation, and the nature of black holes. These examples help to make abstract concepts more tangible and relatable for students. Interactive simulations and visualizations of gravitational wave events have become popular educational tools. These resources allow students to explore the dynamics of black hole mergers and the resulting gravitational waves, enhancing their understanding through hands-on learning. Gravitational wave science has inspired a new generation of educational materials, including textbooks, workbooks, and online courses. These materials provide detailed explanations of the theory and technology behind gravitational wave detection, enriching STEM education. Educational institutions have developed special programs and workshops focused on gravitational wave astronomy. These initiatives aim to engage students with hands-on activities, such as building simple interferometers and analyzing real data from gravitational wave detectors. The inclusion of gravitational wave research in STEM education highlights the interdisciplinary nature of modern science. Students learn how physics, mathematics, engineering, and computer science converge in the study of gravitational waves, fostering a more integrated approach to learning. Outreach programs associated with gravitational wave observatories like LIGO and Virgo offer students opportunities to interact with scientists and visit the facilities. These experiences provide valuable insights into the day-to-day work of researchers and the technologies they use. Gravitational wave science encourages critical thinking and problem-solving skills. Students are challenged to understand complex phenomena, interpret data, and develop their hypotheses, which are essential skills in any STEM field. The excitement generated by gravitational wave discoveries helps to attract students to STEM fields. The allure of exploring the universe's mysteries and contributing to groundbreaking research motivates many young people to pursue careers in science and engineering. Gravitational wave research projects often involve collaboration between schools and universities. These partnerships provide students with access to advanced resources and expertise, enhancing their educational experience and preparing them for higher education and research careers. Graduate programs in physics and astronomy have expanded their offerings to include courses and research opportunities in gravitational wave science. These programs prepare the next generation of scientists to contribute to this rapidly evolving field. Public lectures and science festivals featuring gravitational wave researchers provide additional educational opportunities. These events reach a broad audience, including students, teachers, and the general public, promoting a culture of lifelong learning and curiosity. Online platforms, such as YouTube and educational websites, host numerous videos and tutorials about gravitational waves. These resources are freely accessible and help to democratize education, making advanced scientific concepts available to anyone with an internet connection. Gravitational wave science has also influenced STEM competitions and science fairs. Students are inspired to undertake projects related to gravitational waves, whether it's developing new detection methods or creating models to explain the phenomena, showcasing their creativity and scientific understanding. The integration of gravitational wave discoveries into STEM education fosters a deeper appreciation for the scientific method and the collaborative nature of modern research. By studying these groundbreaking discoveries, students gain a better understanding of how science advances and the impact it can have on our knowledge of the universe. Gravitational wave research has opened up numerous interdisciplinary research opportunities, bringing together scientists from various fields to solve complex problems. This collaboration spans physics, astronomy, engineering, computer science, and more. In physics, gravitational wave research integrates concepts from general relativity and quantum mechanics, challenging researchers to develop new theories that unite these two fundamental frameworks. This pursuit fosters collaboration between theoretical and experimental physicists. Astronomy benefits from gravitational wave research by combining electromagnetic observations with gravitational wave data. This multi-messenger approach allows astronomers to gain a more comprehensive understanding of cosmic events, such as black hole mergers and neutron-star collisions. Engineering plays a crucial role in developing and improving the detectors used in gravitational wave research. Engineers work on creating more sensitive instruments, advanced vibration isolation systems, and innovative technologies to reduce noise and enhance detection capabilities. Computer science is essential for analyzing the vast amounts of data generated by gravitational wave detectors. Machine learning algorithms and artificial intelligence are employed to sift through the data, identify potential signals, and differentiate them from noise. Gravitational wave research also intersects with data science, where researchers develop new statistical methods and computational tools to analyze and interpret the complex signals. This interdisciplinary effort improves the accuracy and reliability of gravitational wave detections. Collaboration with materials science is vital for advancing the technologies used in gravitational wave detectors. Researchers work on developing new materials for mirrors and coatings that reduce thermal noise and enhance the performance of the observatories. In mathematics, gravitational wave research involves solving complex equations and developing models that describe the behavior of space-time and gravitational waves. Mathematicians contribute to the creation of accurate simulations and theoretical frameworks. Astrophysics is enriched by gravitational wave discoveries, which provide new insights into the formation and evolution of compact objects like black holes and neutron stars. This interdisciplinary collaboration helps to refine models of stellar evolution and cosmic history. Gravitational wave research also intersects with cosmology, offering new ways to study the large-scale structure of the universe and the early moments following the Big Bang. Cosmologists use gravitational wave data to test models of the universe's expansion and the nature of dark matter and dark energy. Geophysics and environmental science contribute to improving gravitational wave detectors by studying and mitigating environmental noise sources, such as seismic activity and atmospheric disturbances, that can affect the sensitivity of ground-based observatories. Interdisciplinary collaboration extends to education and public outreach, where scientists work with educators and communicators to develop programs and materials that explain gravitational wave science to diverse audiences, inspiring the next generation of researchers. Philosophy and ethics also intersect with gravitational wave research, prompting discussions about the implications of these discoveries for our understanding of the universe and our place within it. These interdisciplinary dialogues enrich the broader cultural and intellectual context of scientific research. Collaborations with international space agencies and observatories expand the scope of gravitational wave research. Space-based detectors like LISA will complement ground-based observatories, offering new opportunities for interdisciplinary research and discovery. The interdisciplinary nature of gravitational wave research fosters innovation and creativity, driving advancements across multiple fields. By working together, scientists from diverse disciplines can tackle complex challenges, pushing the boundaries of our knowledge and understanding of the universe. Ethical considerations in space exploration are becoming increasingly important as our capabilities and ambitions expand. One of the primary concerns is the environmental impact of space activities, both on Earth and in space. The launch and operation of spacecraft can contribute to pollution and climate change. Space debris is another significant ethical issue. The accumulation of defunct satellites and other debris in orbit poses a threat to active satellites, space missions, and the safety of astronauts. Addressing the problem of space debris involves responsible planning and the development of technologies for debris removal. The potential for biological contamination is a concern when exploring other planets and celestial bodies. It is crucial to prevent the contamination of other worlds with Earth life, which could compromise scientific research and potentially harm extraterrestrial ecosystems. Conversely, bringing extraterrestrial materials back to Earth poses the risk of introducing unknown biological agents. Strict protocols and containment measures are necessary to ensure that any samples returned from space do not pose a threat to Earth's biosphere. Ethical considerations also extend to the potential exploitation of space resources. As interest in mining asteroids and the Moon grows, it is important to establish regulations that ensure these activities are conducted responsibly, sustainably, and equitably. The involvement of private companies in space exploration raises questions about access and ownership. Ensuring that space remains a domain for the benefit of all humanity, rather than a few wealthy entities, requires international cooperation and regulation. Human space exploration brings additional ethical challenges, particularly concerning the health and safety of astronauts. Long-duration missions, such as those to Mars, pose significant risks to physical and mental health, requiring robust support systems and ethical decision-making. The potential colonization of other planets raises questions about the rights and governance of future space settlers. Establishing ethical guidelines for the treatment and governance of space colonies is essential to ensure fair and just practices. The search for extraterrestrial intelligence, SETI, involves ethical considerations about how we should respond if contact is made. Deciding on behalf of humanity about communicating with other civilizations requires careful deliberation and a globally representative approach. The ethical use of space technology for military purposes is another concern. The weaponization of space could lead to conflicts and destabilize international relations. Promoting the peaceful use of space is a key ethical imperative. Ethical considerations also include the cultural and philosophical implications of space exploration. The potential discovery of extraterrestrial life or the colonization of other planets could profoundly impact our understanding of humanity's place in the universe and our responsibilities as stewards of life. Ensuring diversity and inclusion in space exploration is an ethical priority. Efforts must be made to involve people from all backgrounds and nations in space activities, ensuring that the benefits and opportunities of space exploration are shared equitably. Space exploration often involves significant financial investments, raising ethical questions about the allocation of resources. Balancing the funding of space missions with addressing urgent issues on Earth such as poverty and climate change requires thoughtful consideration. The development of international treaties and agreements is crucial for addressing the ethical challenges of space exploration. Collaborative efforts to establish norms and regulations can help to ensure that space activities are conducted responsibly and for the common good. As space exploration advances, continuous dialogue about ethical considerations will be essential. Engaging scientists, ethicists, policymakers, and the public in these discussions will help to navigate the complex ethical landscape of space exploration, ensuring that our ventures beyond Earth reflect our highest values and aspirations. In this video, we embarked on a fascinating journey into the world of colliding black holes and gravitational waves. We began by exploring the fundamentals of black holes, including their formation, types, and key properties. Understanding these basics provided a solid foundation for delving deeper into the complex phenomena associated with black hole collisions. We then discussed gravitational waves, the ripples in spacetime that these colossal events generate. We covered their discovery, the critical role they play in astrophysics, and the sophisticated detection methods and technologies, such as LIGO and Virgo, that have made observing these waves possible. These instruments have opened new windows into the universe, allowing us to witness cosmic events that were previously hidden from view. The video also examined the detailed process leading to black hole collisions, including the orbital dynamics of binary black holes and the immense energy emitted during these cataclysmic mergers. We learned how the spins and masses of the colliding black holes influence the final outcome and the gravitational waves they produce. In our discussion of major observatories and instruments, we highlighted the collaborative efforts of international projects like LIGO, Virgo, and future missions such as LISA. These collaborations have significantly advanced our understanding of the universe by enabling more precise detections and a deeper analysis of gravitational wave signals. We explored the profound insights that gravitational waves provide into general relativity and the fundamental nature of space-time. This included testing Einstein's predictions and addressing complex theoretical challenges like the black hole information paradox. The exploration of quantum gravity theories offered a glimpse into the future directions of this cutting-edge research. The video also touched on the broad impacts of gravitational wave discoveries on cosmology and our understanding of the universe's evolution. These observations have implications for our knowledge of the early universe, the rate of cosmic expansion, and the formation of heavy elements, illustrating the far-reaching significance of gravitational wave astronomy. Finally, we discussed the influence of these discoveries on popular culture, STEM education, interdisciplinary research, and ethical considerations in space exploration. Gravitational wave science not only advances our knowledge, but also inspires and engages a global audience, highlighting the interconnectedness of scientific discovery and societal progress. If you enjoyed this video, please like and subscribe to our channel for more in-depth explorations of fascinating scientific topics. Don't forget to check out the rest of our videos, where we dive into a wide range of subjects that reveal the wonders of the universe and the cutting-edge research that continues to expand our horizons. Thank you for watching.